So we can start with the. Okay. So we can start with the second last session of today. So again, it's nice that almost all people are in person also for this session. And this is a session about multi-robots systems, and the first speaker is Dinesh Thakur, and we'll talk about a swarm of inexpensive heterogeneous microaerial vehicles. Please.
Thank you, Cosimo. Hi, I'm Dinesh. I'm from the GRASP Lab at University of Pennsylvania. This is a collaboration with Model AI, which is a startup which we are tied up with. Just given that we have a diverse crowd here, I'll just give a little bit of background on a bit of swarming and single MAV. So it's started in 2009 when we had a single aggressive quadrotor motions in motion capture. Then later in 2011, we showed multiple drones, again doing formation flight in motion capture. And as time progressed, we had like a lot of industry and a lot of amazing drone shows coming out with GPS-based. Intel made a record back in, I think, 2018, showing around 2,000 drones in formations and with external positioning. So this was general trend with using external positioning to control your drones. In single MAV, trying to move towards fully autonomous onboard sensing and compute, we started doing it in 2000, again back in 11 with a LiDAR and an IMU-based solution. Further, great work by other teams, by ETH Zurich, CMU, and then recently all the commercial drone applications by DJI and Skydio have really pushed the limits forward on the single drone autonomy. Then looking into the multi-MAV stuff, we started with starting around 2 to 3 drones in our lab. When later in around 2016, we showed we can do a swarm of 20 MAVs with just purely onboard VIO. Here you can see, I think the video it's slight. I didn't realize the resolution is wrong here. But we could do 20 MAVs in outdoor just using positioning with the VIO-based onboard, and this was completely onboard. Further, now later on, we have sorry about that. We have works by other like ETH, which started earlier, then Hungary and Delft really pushed the boundaries on this. But as you can see, the number of drones here are still in order of tens of drones. This paper I like. This is a survey which kind of gives you an overview of what's the current trend. And as you can see, it's nicely categorized into 3 categories. We have the centralized with external positioning. We have decentralized with external positioning, with onboard sensing with order of 10 to 20 drones that I just showed. And then fully onboard computing with complete decentralized control, the number of MAVs is still order of like 2 to 3 or maybe a maximum 4. People are still trying to push this. So ideally, we want to push this blob here and towards the upside and make them more fully decentralized. Single MAV challenges we all know nowadays. We want to push the size of the drones towards smaller and increase the autonomy. These are some of the previous works from our lab. For multi-MAV, this is what I'm more looking into is we still want to move towards no external infrastructure. We want to avoid GPS. We would like to be able to deploy them rapidly. If you know, working with multi-robot system, deployment takes a long time. So we would like to reduce the deployment time, communication to have robust MAV communication to do decentralized control. That is another challenge. And distributed control. And finally, we want to add some sort of heterogeneity in our sensing modalities. Because just what a single sensor can do, if you have multiple different kinds of sensing, we could do much more tasks. So towards this end, we collaborated with Model AI. I will not go into the history of the company, but this is a single credit card size board. It's based on the Snapdragon 821 platform. If you think of a cell phone processor back in 2016, that's the compute on this. It's still pretty old compute on board, but it fits. It's a very tightly integrated board. We have 2 redundant IMUs. We can couple it with 4 cameras and some time of flight sensor. The good thing is everything is fit in this compact form factor. So based on the compute, we went ahead and built a swarm of 3 different size of platforms. Here we have a 400-gram platform, another 230-gram platform, and the most recent one is like a 185-gram platform with a thrust-to-weight ratio of 4:1. So it's using the same compute, but a different heterogeneity. We are showing a heterogeneity in the size of the MAVs. For sensing, we could add, with the same board, we could add a thermal camera, we could add a 4K, a stereo pair, as well as time of flight on the same package. Further, to improve the heterogeneity in communication, typically wireless communication, we have a single access point, but to have a fully distributed control, or decentralized control, we would like to have a mesh network. 802.11 Wi-Fi does provide mesh network, but we thought we would add a redundant Zigbee-based mesh network, which allows a longer range than the Wi-Fi, but has a lower bandwidth. So this nicely complements the Wi-Fi system that comes with the voxel board. So all of this package basically fits down to 63 gram with the compute, your sensors, as well as the communication payload. And so what is the capability of such platform? This was presented at the previous Iser. We could take this platform and fly in completely dark environments. This is one of the middle range platform. We just fitted with some LEDs, and we could fly it in low fog. We had a nice presentation how to do state estimation in fog, but we could show that we could fly in low, not super dense fog, just with onboard payload of lighting and sensing, doing obstacle avoidance on this board. Further, this work is still not published. We're still working on this. This is just the same MAV doing a simple exploration task. We would like to be able to, this is simple frontier-based exploration, just showing that we can do this on board of this same credit card size platform. Moving on to the actual experiments that we are doing. So we would like to have this, as usual, videos. Great. Sorry about that. Let me just play it from the. Really sorry about that. So, moving on. So we would like to not be needing any external sensing required for localization. So COVID really highlighted that we need to move the robots out of lab, and this was a challenge for us particularly. We were shut down for 6 months. So this is my home. So what we did is we could just take a fiducial tag, place it in the environment, and use that to get a global reference for these MAVs. And this way we could just perform these experiments anywhere instead of tied to a lab with motion capture or any other external sensing. And this work just shows a simple concurrent-based assignment and planning. This is nothing new. It's a simple centralized control policy, but the robots are fully localizing themselves with this respect to tag and doing the same thing over and over. And then this enables us to do experiments outside of the lab. So moving on, we just showed the same framework basically can work on different sizes of the platform that I just presented. We have here same 5 MAV platform. Then we moved on back to the lab, and we could do more experiments with a larger area. And then this is with the same work with another platform. So let me just stop it there and move on to the slides, if they allow me. Great. Back to the slides, yes. The slides are not working. There. So this work is more of an experimental test bed rather than any novel algorithmic work. So what were the applications where we could use this such a heterogeneous set of MAVs? One application that we are working towards is generating Wi-Fi heat maps. So we showed the exploration task. So if your MAV is exploring and collecting Wi-Fi information at the same time, we can just build a heat map of a building. So this is an interesting work that we have, but we would like to do it with multiple if you have a larger building to cover much larger areas. Another application which a student showed with this is, and the videos have stopped working completely, sorry. We applied this same work to the graph neural networks for a decentralized sensor placement of the MAVs. you can learn this decentralized policies which would mimic similar to a Lloyd's algorithm of sensor placement. How are we doing on the time? So, oh, yeah. So just to summarize now that I'm running out of time, so we are trying to lower the barrier to entry to make such experiments happen and push this outside of our lab towards this. And so Model AI is the company which is trying to, so we have completely open sourced the reference platform, but not everyone wants to build them, so you can go out and purchase this platform right now, or we have this completely CADs and everything open sourced. We showed that we enabled heterogeneous sensing and communication payload under 63 grams, and we can completely do this onboard autonomy and try to push the boundary in this multi-sensor work. Let's see if this works. So just a food for thought. You probably have seen this. This was recently in one of the country where there was a drone show of around 200 or 300 platform, and then they just started falling out of the sky. Just a food for thought. Why we would need to do more towards more decentralized and rather than a centralized based policy. And with that, I would like to thank you. My computer is frozen. Yeah, that's all. Sorry.
Okay. Thanks for. I can speak with this one. I think. Okay, great. Thanks for the nice presentation. Any questions from the audience? Yeah, we have a question there. Nice handling of.
Thank you very much. It was really interesting to see like everything this on board and based on VIO. Actually, I have two questions. The first one is, are these drones available to buy for now or?
Yes.
Okay.
So by end of this month, they're almost in pre-production. You should be able to buy it, or if you prefer, we are also making in the CAD, which is an available where you should have tried to build on your own.
Okay, perfect. My second question is, if we need to do this swarming without, is there a way to do it without this, the marker on the ground? And do you work on this? And how do you think it will be in the future?
So one of the slides I hide it in interest of time. So there's one work we just presented earlier in this session about relative localization. So you could use something like that, and we are working towards one of the students is working where you could do relative localization between the MAVs, and that you can use instead of the single tag.
Thank you.
So thank you very much, Dinesh. Let's, in the interest of time, let's move to the next speaker. Paul, can you come here? Thank you very much. So while Paul is setting up, I will start introducing him. So Paul Mutter, he will talk about, very nice title, sailing a boat through a macroscopic smart fluid composed of a robot swarm. Super fast. You have 12 minutes.
Okay, awesome. Thank you, Kazimo. All right. This is my work, as Kazimo said, sailing a boat through a macroscopic smart fluid composed of a robot swarm, where we present a novel locomotion method in a heterogeneous ground swarm. I did this work with Zachary Hoover and Michael Odie at the University of Maryland College Park. So our project started with or it was inspired by rather, a paper called Magnetic Swarm Control of Microorganisms that was published in 2017 by Sue Kim et al. In Microbiorobotics, second edition. In that paper, the researchers fed some microorganisms iron filings, and which essentially made them magnetic, and then they could control the organism's direction of swim in a fluid. Aaron Becker was an author on that paper, and he and Dr. Odie got talking about doing something similar, but with robots. And they thought about maybe getting something, maybe we can call it a boat, in this fluid with all of our magnetic agents, and maybe the boat could manipulate the fluid to navigate through the fluid. So the boat uses the particles in the fluid to move itself through that fluid. All right, so for our implementation, we used kilobots. If you're not familiar with kilobots, they're very tiny little robots, about 3 centimeters in diameter, and they move by vibration, though very slowly. And they can send and receive 9-byte messages in a 20-centimeter radius. They can judge the distance from the sending bot that sends a message, but the receiver cannot judge the relative direction to that bot. So our robotic swarm fluid is made up of these kilobots. Each agent can be thought of as a fluid particle, and each agent has the full range of kilobot motion. And for the purposes of this problem, those swarm bots can only receive messages. They do not send messages themselves. The boat is a piece of styrofoam with a kilobot embedded in the bow and the stern, or each magnetic pole if you prefer. They cannot move themselves, but they send infrared messages to the swarm to instruct that swarm and hopefully get that swarm to move it. So how does this motion work? For forward motion, we were inspired by bar magnet field lines. You can think of the stern as the positive end of a bar magnet and the bow as the negative end. So the stern attracts the kilobot particles and the bow repels them. The swarm bot detects which pole it is closer to and acts accordingly, either moving towards the pole or moving away from it. This forward motion scheme actually influenced the shape of our boat. So any bot moving towards the stern, or the positive there, kind of squeezes the boat forwards. I'll have a video of that a little bit later, but it influenced the teardrop shape. And you can kind of see in the bottom right of my slide there, we've got maybe a potential energy graph around the boat for forward motion. So a kilobot in the position of any of those arrows would try to move in that direction for forward motion. Turning is a little more difficult, and really depends on the boat design. So at first, we tried to get a boat with no rudder to turn by having all of the bots in its neighborhood just orbit the boat. So for a left rotation, as you can see in the top left of the slide, all of the bots would orbit the boat in a counterclockwise direction and attempt to swirl it around in a way. Informal development before formal testing showed that this didn't work well at all. So we added a rudder to the boat, as you can see in the top right, where the bots would then, to rotate the boat, orbit each pole in opposite direction. So for making a left rotation, I'm sorry, is something wrong? Do you want me to? Okay, sure, okay. Oh, I'm glad he's awake. Holy crap. Okay. But all right, so where was I? All right, so for a left turn, the bots would orbit the bow or negative pole clockwise, and then the stern or positive pole counterclockwise, and rotate the boat pretty much around the axis of that positive pole there. All right, for our experiments, we had 3 boat designs, 1 boat with no rudder, 1 boat with a 7.5 centimeter rudder, and 1 boat with a 15 centimeter rudder. The rudders were 3D printed with an emphasis on lightness and stellotaped to the positive end of our boat. And the bodies of the boat are made in styrofoam, and any differences in the symmetry or inside cutout of the boat were not relevant to the experiment, but relevant to the fact that I'm bad with scissors. So the test environment was a 90 by 120 centimeter whiteboard on a professionally leveled billiards table. Kilobots work well on whiteboards because they're smooth and the kilobots can walk across them easily. Whiteboards also reflect the infrared messages that are sent by the kilobots very well. So most experiments done with kilobots happen on whiteboards. I suspended a bunch of LED lights over the whiteboard and controlled them and was able to control the relative or ambient light level of my test bed using a series of buttons with 4 set presets. One preset for ambient light corresponded to the boat telling its neighboring bots that it just wanted to stay still. One light level corresponding to telling the bots to move it forward, and one level for left and right rotations. So for our formal tests, I would place the boat in a sea of about 75 bots. I would turn on one mode via one light level, and there was no motion correction allowed in these preliminary tests. So for example, if I was trying to test the boat's ability to move forward and saw it turning left, I couldn't correct and make it turn right. I just let it do that mode until the conclusion of the test. And if a bot was too far away from the boat during these tests, it would move randomly. Each boat design was tested for forward and rotation tests multiple times, and the time it took to complete those tasks were averaged. So for a forward test, I simply tested how long it would take for the boat to move from one line to another parallel line 30.5 centimeters away. I don't care what direction the boat was pointing once it broke that other line, or really where on the other line it ended up breaking the point. Just I tested whether it would at some point, and then took the time it took to make that traverse. Rotation, and it turned out that at the end of those forward tests that the boat with the 7.5 centimeter tail, so the short tail, was the quickest. Rotation tests, I tested how long it would take the boat to rotate 90 degrees. So i.e. go from perpendicular to a line to parallel to it. And the shortest rudder was the fastest during those tests as well. Unsurprisingly, the boat with no rudder wasn't able to complete that. As I mentioned before, we had some difficulty getting those to turn at all. Okay, here are some videos of the forward and rotation tests. Forward test on the left, rotation on the right. And yeah, every once in a while you'll see my arm darting in there to grab dead bots and get them charging. It wasn't to influence the test in any way. All right, so once the forward and rotation tests were complete, I graduated that short-tailed robot, which had proved the fastest in both, to a more complex test. So in this test, I attempted to drive the boat through a Z pattern on my test bed. Similar conditions to the forward and rotation trials, except this time I get to steer the boat by changing the light levels to in whatever direction I feel will make the boat complete this pattern quickest. So you'll see a video in a second, and you'll see the light levels changing. That's me changing the light levels to try to get it to move in this Z pattern as quickly as possible, and the only goal was to go through that pattern in order. And yeah, over 5 trials, it took a little just over an hour on average to complete this test. All right, so while this video is playing, I'm going to go over some conclusions of our work. We concluded that we can reliably sail a boat through a smart fluid by inducing the fluid to create a local force gradient around the boat, and we show that we can do that repeatedly. The Z-path test shows that movement can be chained together, And that motion is still possible as the bot count depletes. So you'll notice as this video goes on, more and more bots will wander away from the boat and get trapped at the edges of the work surface. And there will be fewer and fewer in the neighborhood of the boat, and that motion is still possible even though it takes a really long time. We show through this test that we can reconfigure the smart fluid on the fly to suit the local needs of the boat. We also show that rudder size affects the boat's turning and forward motion ability. The rudder provides, we think, or posit, the particle bots a place to engage on the boat during forward motion and provides a lever for rotation. Unfortunately, our very simplistic turning and forward motion methods were not able to turn a boat without a rudder, but we just think that our localization scheme was not precise enough to accomplish that. Yeah, is this video, well, there it is, there it ends. Thank you so much.
Thanks, Paul. Any questions from the audience?
Wow, I did that good of, oh, there we go, okay.
Hello, thanks for the very nice presentation. I was just wondering, could you speed it up by having more kilobots, or?
Yes, and my advisor did have more kilobots in his lab, but didn't trust me to take home all of them. So I was left with only about 100. Another thing I probably shoulda, coulda, woulda done is reduce the workspace size a little bit to keep robots from wandering away nearly as much.
Thanks.
Okay. Any other questions from the audience? Okay, so then again, in the interest of time, we're a bit running late. Thanks again, Paul. Very nice presentation. And the next speaker is Kagan Erunsal, and he will present his work about nonlinear model predictive control for formations of multi-rotor micro-aerial vehicles, an experimental approach. I will tell you when it's 2 minutes from the end. Okay, is that fine? Oh, it's disappeared. Okay, great.
Thank you very much for the introduction. My name is Kaan Erunsal. I'm from EPFL Lausanne and IST Lisbon. So today I will present you the nonlinear model predictive control for formations of multi-rotor micro-aerial vehicles. And actually this work is evolved since we submitted the paper. If you have any detailed question, please ask me after the presentation. I will gladly answer. So we'll start. The missions defined for microaerial vehicles are getting challenging every day. I can give you some examples like scientific exploration, construction, and the search and rescue. And usually we have two types of remedies for this problem. One is the advanced control methods that usually they are performant, scalable, but we have design difficulties and the computational cost. And either we choose this one or we went to single robot to multi-robot setup, and these are usually robust, but there are implementation complexities and safety concerns related with them. So why not both? And then we have a time-consuming implementation, and it is very challenging to validate. So before going into details of our methodology, I would like to give you a multi-robot example, which is the control, formation control that we choose as a user case. We chose this because we think that this is the main building block of many coordination problems, and we adopted a leader-follower approach with 3 quadrators. And the team actually does trajectory tracking, and you can see the scenario on the bottom. So as an advanced control algorithm, we choose decentralized non-linear model predictive control. As you know, this is one of the advanced optimization-based algorithm. It relies on the mathematical model of the system, and you choose a horizon and you optimize your problem based on this horizon. Then you apply only the first input and the time window shifts, and you apply the procedure again. And it is decentralized because we would like to work, we don't want to rely on with the centralized approach while using multi-robot case. And this approach is architecturally flexible and they satisfy the constraints and the performance at the same time. It is a multi-objective nature and scalable. And I mean, there is no communication and it is very easy to formulate. However, it is computationally expensive, an accurate model is needed, and it is usually very difficult to implement on board. So actually, this paper stays in this intersection between model calibration, decentralized nonlinear model predictive control, formation control, and microaerial vehicles. In other intersections, you can see some papers with the single robot and the multi-robot case, but to the best of our knowledge, this is the first work done in this intersection. So, our technical approach starts with mathematical formulation and abstract simulation, usually, for example, done in MATLAB or Python. So, this is very important to understand the solver characteristics and the model that you use. Then we propose to go to high-fidelity simulators like Gazebo or VBots with some plugins like aerodynamic model that you can actually use very reliably. And this, especially simulator, is also important to go to real implementation because usually the code that you use are very similar to real implementation. For example, if you use this kind of simulators as a plugin in ROS. So the next step is do calibration experiments. And we did a bunch of experiments actually to do a system identification and to really understand the model that we have. Then we go back to, again, abstract simulation and the high-fidelity simulation to update them. So the next approach is to do single robot experiments. And the feedback based on this, we update the model again. And then we will be able to very easily go to multi-robot experiments. So this process was really smooth. So this is the architecture that we have. For all the leaders and the followers, we have a similar approach. We have a high level in nonlinear model predictive control trajectory or relative trajectory controller. And in a cascaded way, we have attitude controller. We actually really want to decouple these two because these are working in different frequencies. And nonlinear MPC is actually computationally very expensive, and this actually makes us to work in a very good frequencies. So there's an extended Kalman filter to estimate some states, especially the relative position, and the filter out the noise on the data. So here we have the optimization problem that is running. So we have here as a cost function stage and the terminal cost function. And the terminal cost function is required for the stability of the system. And we have a system model. This should be as much accurate as possible. And we have some inequality constraints. These are usually the actuation limits, comfort constraints, or for example, limits in the relative position. And we have, at the end, terminal constraints, which is again required for the robustness and the stability of the MPC. So here in the leader, we have position and velocity errors, input rate, and the nonlinear self-model of the system. To have a nonlinear model is, I think, is very critical here. And for followers, we have relative position and velocity, input and their rates, and nonlinear self-model, and the constant velocity model of all your neighbors. So, I mean, this is an updated model, this works decentralized. In this work, it is not included, but what we are doing now, actually, this number of neighbors is updated every time, and when you have different models, so it works completely decentralized. And the chosen coordinate frames are really critical here in order to have a smooth transition with the estimator. So, and how we solve this problem? We apply an SQP-based real-time iteration. First, we discretize the model. Then we sequentially approximate the model by linearization. Usually, the model that you have is very sparse, and you need to apply some condensing methods. Then you solve each your quadratic program. And based on your optimality conditions, iteration limits, and the CPU time that you have, actually you want to terminate your algorithm. So the first part is done by high-efficient C code generation by use Akado, and the second part is the outer-level algorithm. So first, and as I told you, there are some parameters that we need to calibrate, and we did it in 2 stages. First is the model identification that it is required to work with the MPC, and the second part is the simulation calibration to have a high-fidelity simulator. And basically, how we identify this parameter, basically digital scale and attitude subsystem gains, closed-loop position control test, and regression. And throttle to thrust gains, torque constant, thrust constant, we use RC benchmark propeller setup to identify the propeller characteristics. Inertial F2 double arm pendulum setup, and the lumped PID parameters for attitude controller, we did it in the closed-loop test in simulation. So at the end, we have a bunch of parameters that can be used. And this is the quadrator that we have. It is a helical storm drone 4-frame. It is nearly about, with all components, 1.5 kilos. It is a bit large drone because we need this hardware to run the MPC, basically. As an autopilot, we have Pixar Cube Orange. We have Raspberry Pi. We run everything on board. Then we updated this board to a more recent one. And the Pixar optical flow for velocities and the mock-up markers to generate position and the relative position. Now we are going to do more in visual and the relative sensing mechanisms, but when we do this paper, we used mock-up. An external digital compass because we do the experiments inside and we need some yaw position, accurate yaw position to control. So this is the results of the calibration experiments. As you can see, they are really close. On the right, you can see the trajectories in real and simulation. And in average, we obtain really small error, like 6 centimeters for these calibration experiments. And this high-fidelity simulator is working in VBOT as a plug-in to ROS. So then we go back to simulator again, and with these parameters at hand, we did a formation experiments with 3 drones. So as you can see, the leader actually does the trajectory tracking, and the other leaders actually, other followers are follow them. So on the right, you can see the average norm error of the formation. We obtain very small, like 5 centimeter error in steady state and 0.35 in transient. So, and the optimality conditions show that the really non-near program converges to SQPs. So, and then we go back to field and we just some tests with manually translated leader to eliminate the aerodynamic effects. And we actually moved this quadrator in a 3-meter cube area and did some experiments with it. And at the end, we reach 0.11 meter norm error. And optimality conditions are really small. This is actually really comparable with the simulators. However, when we go back to do experiments with autonomously flying leader, and we had to do this with only 2 in the COVID situations, I mean, it was, all the facilities were locked. But actually this shows a kind of a good baseline of our work. So what happened, actually, we saw an increasing really error in the formation errors. It is because the mutual aerodynamic disturbance between the drones, and these drones are big compared to like the small drones, and they have really good like a downwash effect for the other drones. So, and at the end, our error goes up to 0.44 meters, and the optimality measures are increased a lot. So, at the end, what was our conclusions and outlook? Even the uncalibrated high-fidelity simulator was really beneficial to go to multi-robot experiments. So, we were able to use the same code in both this high-fidelity simulator and the real experiments. And however, the reality gap was significant, especially these model-based approaches. We have to apply 2 strategies, which is the model identification. The second one is the simulation calibration. However, at the end, transition to multi-robot case was really smooth. And we saw that this mutual aerodynamic disturbance should be either modeled or compensated some way. And now we are working on the adaptive L1 strategy actually to improve the performance, and it seems it is working. And also to automate this process, we are also working on revise the methods, online learning methods to be explored. Thank you very much. If you have more detailed questions, you can go to this website or just send me an email, and I can accept all questions. Thank you.
Thanks, Gagan. Any questions? Okay, I see one hand.
This is a bit more of a technical question, but what do you use to get your MPC solutions on board in time?
Yeah, I mean, the reactive approaches is okay, but if you would like to have like much better performance, accuracy, if you are doing like fast flights, especially if you go to, for example, do formations with agile flights, these reactive methods are usually doesn't plan ahead, and they have some problems. So the previous PhD student actually tried to do this with reactive method, and he saw that without planning, some scenarios he was not able to do it. So actually we need to put the MPC on it to have much better performance in these agile scenarios that we can encounter in daily life.
Thank you.
Yeah. Thank you.
No other question. I have a question myself. So about the stability of the whole system, you briefly mentioned something at some point. So I wonder. I mean, it's a distributed nonlinear setting.
Yeah.
Can you prove something?
There are some proofs, not in this paper, but in another paper which is under review. Actually, by adding some contractive constraints on it, you can prove the stability of distributed system. But these are practically a bit, the solution converges very slow. So in practice, usually we don't use actually this kind of conditions. But in theory, especially with the contractive constraints, it is possible to prove stability.
Okay. So thanks a lot, Kagan, again, and Carlos. You can, so next speaker is Carlos Nieto Granda, and he will present his work about distributed heterogeneous multi-robot source seeking using information-based sampling with visual recognition.
Hi, my name is Carlos Nieto. So I'm going to present my work. It was the last chapter of my thesis when I was in UC San Diego. Currently, I'm in the Army Research Lab. This work was worked with Shengye Wang, Vikas Diman, John Rogers III, and Henry Christensen. So our goal is to have these very powerful and amazing devices that they can map everything in 360 degrees in real time, giving us all this information that we need, like semantic information, landmarks, and so on. But the reality is this one, that we have one robot that is actually teleoperated or semi-autonomous mode, and it can only solve one task in this time. And if you can see in the video, they have two operators just to use this kind of robots. So that's something that we don't like in multi-robot systems, because that means that it's going to be two operators per robot. So if we work to 20, it's going to be like 40 or 80 people. Oops. Sorry. So the main objective was to create this distributed system that allows basically to have independent decisions without a centralized system. So remove all these communications coverage, which means that the robots can be in some areas of the building, get informations, come back and communicate with each other, and start doing the management of resources also for the communication, so they can reestablish the communication that they have. So the problem definition for source seeking is that we have a number of targets. We don't know how many they are. We don't know where is the location for each of them. And we need basically, the only thing that we know is the pose of the robots. So in order to do this, we are basically doing information gathering, which means that we want to maximize the information gain, decrease the entropy, which guarantee that you have all the targets and you can find them. We applied this new coordination strategy, which was basically the management of resources that we present in the previous Iser. In this one now, the robots can actually broadcast two messages. One is that the task was accomplished, so that means that I am free, so the other robots can help the other robots. And the other one is when a robot has problems, or if they need help, they just broadcast like, I need your assistance, and the other robots can help for this one. So as you can see here, this is the renal map. This is with three robots, sorry. So this is one of the robots, so he basically just scan all this area, the other one map this area, and the purple has to map all this one. But this one is a really cluttered area, so it's going to take a lot of time. So when he gets in troubles, the green already finished his task, so he just broadcasts the message, and he can actually map the area, so it's faster. So we run some simulation experiments. This was used our ARL Unity environment. It's a simulator created in Unity and use ROS nodes, and it used our ARL navigation stack, which is basically our framework from the US Army Research Lab, and that's what we have in our platforms. In this case, we were using our mapping system. It's called OmniMapper, and here are the robots that we were using. So we have warthogs, we have huskies, jackals, and drones. So this is an example of one of the simulations. So you can see basically the trajectory of each of the robots. And using the new trajectory, actually the entropy decreases faster. The trajectories that you see in green, that means that was the drone. So in this case, it's like a robot team. So each of the mobile robots has a drone. So when they cannot reach the target, in this case, it will request the help for the drone. We perform also real experiments. This one was in UC San Diego facilities. And I want to show some of the experiments and results that we did in this place. So the mission is basically to explore an unknown environment, look for all the targets. In this case, we want to simulate like a fake IDs. Deactivate the fake IDs and confirm that there are no more IEDs in the environment. To do that, I simulate the reactivity using an Arduino. And because I was not allowed to create a fake ID, I use this toy, which is basically the bomb from Mario Bros. And so that's an ID. How it works, because we were using the DJI drone, there is no computation on board. So the mobile robot was exploring. It creates the plan and the trajectory for the drone. So in order to do that, we use a Mac Mini. So the drone, basically the mobile robot send information to the Mac Mini with a computer and from a phone and so on, and he was going to present like what is the region of the searching area that the drone has to do, which one is the path planning, and where is the possible location of the IED. Now as some people know, I like to complicate my life, so the only order to deactivate the IED is to actually see the eyes of the bomb. So this is experimental setup. So this is one of the buildings, and the blue ones are only reachable by the drone. So as you can see, well, I don't know if you can see it, but one is in the ceiling. The ones are on the table, so there is no chance that the mobile robot can actually see it. And even if you can see part of the body, as I said, if they don't see the eyes, you cannot deactivate it. So this is one of the experiments I'm going to use. So here is the mobile robot. Everything is in autonomous mode. So you can see it's basically listening all the IEDs that are in the environment. So all the 6Bs. One is on board of the robot. So that's basically the reason of this shaking mode. So it found the first one. It'll identify, I'm using pictorial structures basically just to take like a bounding box for the target, for the IED, and he deactivate that one. So the closest one now is on the left, so he's going to go inside of the room. I'm just going to accelerate this. So, so as you can see, the IED is actually over the table. It's in that. It's actually over this cube. So there is no chance that the robot is going to see it. However, the robot is going to try to actually to reach it. So it's going to be going around the table, basically to say this is the possible region where the IED is. So after the robot try to reach it, it's the moment that he requests the assistance of the drone. So now the drone goes, and the drone basically have a Gaussian region where's the probability for the IED to be located, and it sends different trajectories. So it knows that the higher probability where the IED is in this one, so it creates a Gaussian region, and it just sends a trajectory for the drone to go to this area and start exploring. Now, if the drone send the image and it's a part of the body, but it didn't see the eyes, the mobile robot, what it does is to create another trajectory in order to say, well, the face is in the other side, so you have to go around until you deactivate the IED. So that's the message. Okay. So that's all those patterns and paths of the drone. So these environments are really interesting. So as you can see, I didn't change the environment at all. In fact, I did it more complex. So you have robots, you have tables, everywhere the robot has. So it's actually doing obstacle avoidance, looking for those targets, and listening. So the 6Bs, where there's a possible location, and it's just looking where they are, create more regions for the drones, and the drones finish the job. So this is Atkinson's Hall for the first floor. So the environment is really interesting because they have different ways to see the environment. It's really big, so it's really complicated. Another thing that I didn't mention, our mapping system used semantic information from the environment, but in this case, our semantic information was basically everything looks like a lab or like an office. So there was no point to get that information over there because it's full of robots and it's a nanotechnology building. So this is one of the maps. So those are the trajectories of all the robots. And in red is where they require the assistance for the drones. As you can see, this is with the old, not using the new strategy, like communicate and doing the managing of resources for the robots. And this is with the new one. So as you can see, the entropy decreases really fast getting assistance. The best example is here, where the green robot has to go all the way to this part of the building. And when he's actually exploring over here, he requests help because he has to go inside. The blue one was already coming back, so the blue one finished the job. So I tested in different environments, as you can see, more and more complicated. So this is just a mobile robot looking for the IEDs, and this is what the drone is going to see after he finished. So just creating those regions actually helps to look for the next ones. these are the results. This is the result of the map. As I said, they don't know the map, so they actually build all this map, and this is in real time. So the conclusion is that we aim actually to find the policies so we can actually decrease the entropy really fast. We know all the trajectories and we create new paths so the drone can actually find the IEDs. And as I said before, this is a really modularity framework, so you can just add more robots and there is no problem, so it's really scalable. Our future work for this paper, which is the current work, is that we improve the capability of our robots. So now the regions that the robots has to go, they have a bid system that was just presented in SSRR 2 weeks ago. So the robots know like where to go. And now we can actually plug and play with different mapping systems. So right now we're working with Chimera Multi. So we can actually do exploration not only in indoor environments, but also in outdoor environments. This work was funded by, this is through the US Army Research Lab. And with this, that's the conclusion. So if you have questions.
Thanks, Carlos. Yeah, I see one question there.
Hi, thank you. I was just wondering how you define the entropy for this. Is it like an occupancy grid-based mapping thing?
Yes. For this work, yes. In the second version, which is the current one, we're actually using semantic meshes.
Other questions? So I just a curiosity. So how this deactivation thing, identification deactivation thing would look in real life? What would be the operations that you have?
So right now what we want to do is, like, for example, for looking for gas leaking. So we don't want to see like, okay, you have IEDs, look for them. It's just the robots are just patrolling. So you have the robot just looking around. And when it identifies that there is a leak, he can actually send messages to the other robots and they do it.
Okay.
That's one. The other one is rescue missions. And the other one is looking for actually IEDs.
Great. Thanks a lot. So, Joao, can you? So our next speaker is Joao Borges de Souza, and with another very inspiring title. It's To Boldly Dive Where No One Has Gone Before. So you're raising high expectations here. Experiments in Coordinated Robotic Ocean Exploration.
If it works. Okay, so good morning. My name is João Souza. I have more names, including an Italian name. So, and honestly, I'm not crazy about the title. So, so I'll be talking about the exploring fronts with multiple. Oh, sorry, I forgot about this. With multiple robots cruise, an oceanographic cruise that was funded by the Schmidt Ocean Institute. 3 weeks in the Pacific on board the RV Falcor. This is my team, 17 people on board the ship. And we had people from the University Polytechnic of Cartagena, University of Rhode Island, and TNU in Norway, Port University, of course, because that's where I come from, and also Harvard University. And we had collaborators, for example, from NASA, Ames, SINTEF, Portuguese Navy, and MBARI. And last but not least, Kana Raja was my co-PI, and he's a great fan of Iser. So starting with some motivation, Blue Planet, beautiful, but misleading. Why? Because this is the naked reality. So all of Earth's water would fit inside a sphere like this, meaning that, hey, there's not much water, and we really need to be careful about what we do in the oceans. Moreover, we still don't know much about what is going on there. So, for example, Walter Munk said that the 20th century was the century of undersampling. And this is motivation for what we are doing in our lab at Port University. This is an old picture. I need to upgrade this so we have more toys and more people. So we've been designing, building, and deploying autonomous underwater surface and air vehicles for networked operations. We've also been developing the software that enables all of these guys to work together as teams. We operate a lot in lots of different places. We've been to some exciting places. So we run very large-scale exercises. We have deployments from shore, from ships, and also from manned submarines. Actually, we operate also with manned submarines. Skip this. And now let me briefly talk about the cruise. So exploring the Northern Pacific subtropical front with multiple robots. So we deployed from the Falcor. We had multiple AUVs, as you can tell. We also had VTOLs and several ASVs, so 2 sail drones and 1 wave glider. And this was the main goal of the cruise, to demonstrate a novel multi-vehicle system capable of finding, tracking, and sampling features of the ocean with adaptive spatial and temporal resolution. And now, the video.
During this expedition, our team has created a system to conduct oceanographic surveys with unprecedented levels of detail and scale. Approximately 1,000 miles off the coast of Southern California, we are studying the subtropical front. Here, 2 masses of water collide, which generate a unique mix of physical, chemical, and biological features. Before the expedition, autonomous vessels helped us determine the approximate location of the front. When we arrived here, we deployed CTDs to gain a more precise understanding of its spatial dynamics. Our autonomous underwater vehicles, which were specifically designed for this expedition, can cover hundreds of kilometers and stay in the water for up to 50 hours. They travel in a yo-yo pattern, sending real-time data back to the ship every time they surface. Our fixed-wing vertical takeoff UAVs can fly faster and further than quadcopters and carry a variety of sensors. The data our autonomous vehicles collect helps us locate biological hotspots where we conduct more detailed sampling.
We are deploying very advanced technology that needs to be refined through experimentation, and by doing that, we hope to establish some of the foundations for the future of oceanographic surveys.
Okay, so now a few words about our area of study. So we went after the Northern Pacific subtropical front, which is a sharp boundary where cold waters from the north meet warm, salty waters from the south. It's very strong, has a very strong salinity signature, but a weak temperature signature, and it's located approximately 1,000 miles west of San Diego. There were previous studies in the 80s and in the 70s, basically ships, several ships that did something like this, and like this, and this is the place of the front. And some data. This is kind of interesting. You don't need to be an oceanographer to understand there's something going on here. So this is data from one ship track, X distance, Y, salinity, and here you have temperature. And then if you look at these ISO lines, you can definitely tell that there's something weird going on here and here. So it looks as if waters don't mix. Why? Because we have two fronts here. This is the one that we were looking at after, and there's another one further north. In terms of the old assets that we used, so we were using basically SATCOMs for communications with these guys, basically for sending missions and commands, high-level objectives, and also to get data. And then we had Ripples, basically a web-based kind of an application that we could use from the Falcor because we had some very nice SATCOMs, and also from Porto, from what we call the Ocean Space Center. So we had a web-based mission control center. We are operating non-stop, so we operated non-stop for 2 weeks, 4 shifts per day, 2 guys per shift. And this was Mission Control Center in Porto and Mission Control Center on board the RV Falcor. Then again, how to go about addressing complexity? Nothing new about this. So we had a few, let's say, prototypical tasks. One of them is just performing yo-yo maneuvers. The other one was kind of tracking the front, which is not an easy thing to do. This is a huge front, and the signature is a bit strange. Then having multiple AUVs performing concurrent measurements to get a synoptic view of what is going on there. And then the first problem was to find the front. Why? Because this front is very difficult to spot from space for 2 reasons. First of all, it has a very weak sea surface signature. Second, because it's mainly cloudy in the area. So to find the front, what we did was we sent 1 wave collider and 2 sail drones ahead of the ship's arrival. And basically we were looking at data coming from these guys, basically temperature and salinity. And we were trying to find the signature of the front. We did it. We're quite successful in doing that. And now let me tell you a little bit about what we did in the first 5 days. In the background, you see the only sea surface temperature map that we got from the area. So lower temperature, higher temperature. And then these lines represent AUV tracks, color-coded by salinity. And so when we arrived to the position that we selected, hey, this is the front. So we deployed some AUVs there. You can see there kind of AUV tracks. And we thought, hey, this is the front. It's here. But while we were doing this, we moved south with a Falcor, and then something weird happened. Keep in mind that at the time, this SST map was not available. So we went from, let's say, cold, warm waters, cold again, and warm. So something weird was going on. So we decided to go for a mesoscale mapping. These are kind of gives you a sense of scale. And it was by then that we realized that, hey, this was the front, and we were observing a filament detaching from the front. So planning for coordinated ship robotic surveys. So 2 ASVs crossed the front near 30 degrees north, 1 ASV and the other one. And then we decided, hey, this will be our op area. The Falcor was still far away from the area. And then we decided, hey, when we get to the op area, Falcor would go south, will perform CTD casts, and at the same time, we'll have several AUVs performing these kind of motions, collecting data, and simultaneously and concurrently, the Falcor was also collecting data and performing CTD casts. So lots of things going on at the same time. And we kept doing this for several days. And then after this, we got a kind of a good feeling, hey, now we understand what was going on. And then after this, we had just a kind of a few ideas. We had short-range AUVs deploying along the front with biological sensors. The same thing with the UAVs, VTOLs. I'll say more about this. Same thing with the Falcor now that we identified hotspots. So we went there with the Falcor for kind of a CTD casts and other stuff. This is a 3D view of the front. It's quite large. And in terms of data, then again, without going into details, what you see here in background is a product derived from satellite altimetry. And actually, in controls, we are quite familiar with this. These are called finite size Lyapunov exponents that give you the structure or the skeleton of the flow. Superimposed on this, you have, in this case, ship tracks, also color-coded by salinity, and velocity measurements, velocity of the current, okay? And then you can see that there's this very nice, you have these very nice correlations, and same thing with the SST. We also performed very interesting experiments with a VTOL equipped with a DMS sensor. DMS is a gas, it's a proxy for biological activity. And so you can tell that when we were flying close to the front, concentrations were much higher. We also performed automated front detection and tracking, no human intervention here, and high resolution coordinated sampling. So having AUVs with biochemical sensors coordinated with the Falcor, with AUVs, with the UAVs, moving information and collecting data, let's say concurrently in same area, so synoptic measurements.
So we take all these different systems that go beyond the footprint of what a ship can do. They can be 20 miles this way, 20 miles that way, and help us understand the oceans a lot better than we do now.
This was basically key to what we were doing. So extending the footprint of what a ship can do and coming up with new ways of doing oceanography. So the footprint for say our operations was in the order of tens of kilometers by tens of kilometers. And just kind of a quote from Eric Schmidt, basically Schmidt Foundation was paying for this. And some conclusions. So we successfully demonstrated a novel approach to observe the ocean with persistent network vehicle systems. We operated non-stop operations. So our AUVs did over 600 hours, over 1,000 nautical miles, and lots of stuff. And finally, the systems and technologies demonstrated in these cruise are applicable to other frontal regions as well as to other phenomena of the world's oceans. And this is pretty much what I had to say. Thanks very much.
Thanks, Joao. Any question? Yeah, I see already one.
Hey, thank you for the talk.
Thank you.
I'm curious how much, just a guess, how often you're able to do more autonomous operations like front finding versus sort of laying manual paths for yo-yoing. Just a general guess.
That's a very good question, and it was also one of the conclusions from the cruise. So in addition to people from engineering, we also had scientists on board, so marine biologists, oceanographers, and initially those guys were they really wanted to go the traditional way, as you were basically saying. Then they learned along the way, and this was something very important, and I think that we achieved something there. Then along the way, they realized, hey, we can do much more. So for example, I was talking about this kind of front tracking algorithm. It was developed on board the Falcor, and so we started going a bit away from traditional kind of oceanographic sampling when these guys realized that, hey, we can do much more. And towards the end, actually, we had our planning meetings, and I'm pretty sure that if you were, I would say, looking from outside, looking, let's say, at what was going on in the meetings, you couldn't tell, hey, this guy's an oceanographer, this guy's an engineer. So I think that was one of the major accomplishments of the cruise. I should also say that everything went well, and we only had two problems with two servos, which are, let's say,
that's quite remarkable.
Thank you.
Thank you.
Another question there?
Hey, thanks for the nice talk.
Thank you.
I'm not an oceanographer, so maybe it's just a very stupid question, but
I'm not an oceanographer either, so don't worry.
So what do you, so why is this front so interesting? What do you want to get from exploring this front?
Okay, Then again, I'm not an oceanographer, I'm not a marine biologist, but I can repeat what I was told about it. So now I can have a good understanding. So basically, so this is an interface between two different masses of water. And what happens there is you have lots of biological activity there. And people still don't understand much about what is going on there. But to give you more kind of a precise kind of motivation for studying fronts, if you look at, let's say, AIS tracks from ships, in some places in the world you can identify fronts because oceanographic vessels, let's say fishing vessels, typically go to these fronts because there's lots of activity there.
Okay, thanks.
Yeah, wonderful.
Thank you.
A lot of fun. So I'm wondering about samples. Wouldn't it be nice to collect samples? Especially, I mean, in that rich area?
Yes, you're absolutely right. And this was also one of the coordination kind of problems that we were addressing in the cruise. So with the AUVs, we were just collecting, let's say, a kind of data. But with the Falcor, so we were collecting water samples using the CTD rosette, and so we also had there some Niskin bottles or so. So we were collecting those, and then we are still kind of working on the data, collecting the, let's say, trying to make sense of the data that we got from these samples in correlation to the data that we got from these measurements. So, for example, we found lots of interesting stuff, biological stuff there, and then again, a very interesting correlation between locations of these guys and some features that we found by using the AUVs. Thanks very much.
Thanks, Anne. Joao. I see there are other questions, but you will have time during lunch to catch up. Now we have our last speaker, which is online. Let's see, I have to... Okay, great. Can you speak again, sorry? Please?
Can you hear me?
Yes, yes, we can hear you. So, last speaker of the session is Kishiti Goel, and his talk would be about rapid and high-fidelity subspace exploration with multiple aerial robots.
Thank you. My name is Kshitij Goel, and I am a PhD student at the Robotics Institute at Carnegie Mellon. And today I'll be presenting research in multi-robot exploration in subsurface environments and how we can achieve that in a rapid and high-fidelity manner. The motivation behind this work is planetary subsurface exploration. Till date, several subsurface environments have been identified on various planetary bodies in our solar system. The image on the left shows these planetary bodies with the number of potential subsurface environments in the parentheses. For Mars in particular, this number is above 1,000. Prior studies have suggested that these subsurface environments are of astrobiological significance to understand past signs of life on Mars. So far, the exploration missions to Mars have been constrained to either orbital or on-surface operations. Therefore, robotic exploration techniques that allow us to collect data in subsurface environments has been identified as a key capability for future space exploration missions. The first question to ask when deploying such a system is what kind of a robotic system should we use? According to Phillips Lander et al., the caves identified on Mars fall under 4 major categories when evaluated on the basis of access difficulty versus traversal difficulty. The most difficult type of cave to access and traverse are the ones that require vertical entrance and contain non-smooth terrain, as shown on the top right of this plot. The authors then categorize existing robotic platforms according to the same capabilities, access and traversal. Note that the flying robots are towards the top right, meaning that these robots have the highest potential to traverse and access all 4 categories of the cave. And this fact actually motivates us to focus on flying robots in particular for our multi-robot exploration framework. Assuming that we want to deploy these flying robots in our subsurface exploration context, we also need a concept of operations to guide this deployment. The proposed framework is motivated by a concept of operation that was previously proposed by Matthews et al. For a concept mission for Titan. The concept mission consists of a surface station, which we call here a mothership, and a team of aerial robots, which we call here daughtercraft. The aerial robot team has been deployed by the surface station to perform autonomous and distributed mapping and transmit a high fidelity map back to the surface station, and then relay it to Earth via an orbiter. Therefore, there are three communication channels in this concept: subsurface communication, orbiter communication, and Mars to Earth communication. It turns out that the communication bottleneck amongst these three channels is due to subsurface communication. In this concept and in this work, we assume that the aerial robots are equipped with magneto-inductive links, as proposed by Kirishev et al., that can provide a communication bandwidth of nearly 0.1 to 0.25 megabit per second for 15 to 20 meter deep operation for the aerial robot team. Now, there are multiple challenges to address for this concept of operations to be realized. First, as you can realize, is the limited communication challenge. Transmitting raw data on these low bandwidth communication channels may not be feasible at all. Second challenge is due to dynamics and sensing limits of the aerial robots. In practice, maximum acceleration and jerk attainable by these robots is limited, as we know. And also, these robots are usually designed to be light. So the sensors that are put on these robots are usually of a limited range. Third challenge is due to size, weight, and power. The endurance is limited. And lastly, we cannot allow any of the robots to collide with the environment at any cost. For the last three elements, we rely on prior work, and the focus of this talk is going to be towards the limited communication challenge. So to address the limited communication challenge in the exploration context, we first look at some related work as to how prior work has addressed mapping representation and its usage in the exploration problem. There's one important class of exploration planners that rely on information theory. Charo et al. Used an occupancy grid mapping approach for information theoretic exploration. However, transferring the changes to global occupancy grids over time with raw occupancy probabilities is assumed tractable in this scenario without considering the limits on available communication bandwidth. So this cannot address the limited communication constraint that we have, as we will see later in the results. Similarly, there is a recent approach that uses octomaps, which are also known to have lower space complexity than occupancy grids. However, the underlying representation is still discrete and requires a large amount of data to enable distributed information theoretic exploration. In contrast to these two approaches, we leverage the recent advances in Gaussian mixture model-based mapping to allow for compact distributed mapping while remaining amenable to performing information theoretic exploration. So let's do a quick overview of what is Gaussian mixture model-based mapping. So information theoretic exploration with respect to this kind of map is enabled by regressing a local occupancy grid from a global GMM map. A GMM surface model is created using the depth point cloud, as we see here. So in sub-image A, we have a color image coming from a cave environment. And B shows the depth image corresponding to that color image. C has the point cloud corresponding to the depth image. We first partition the point cloud into two separate parts. The free part, which is at the maximum range of the sensor, and the occupied part, where the range of the points is lower than the maximum range. And then we learned two Gaussian mixture models. The red model shown in subimage E is the occupied model, and the black model is the free model. And since this is a generative model, later after transferring it over a communication channel, we can resample it densely to get a representation of the environment. So that's how the GMM model creation works. And for further detail, you can refer to the work by Tapib et al. And then using the GMM models obtained in the previous stage, we can reconstruct occupancy for each robot using Monte Carlo ray tracing, for which the detail can be found in our kind of work too. So the problem here is that GMM creation is expensive because expectation maximization is computationally expensive. And as detailed earlier, we want this to run on computationally constrained platforms. So what we do is we select observation intelligently. Instead of operating on all the depth images in the sequence, we have a geometric heuristic where we check for overlapping volumes of consecutive depth scans. And based on a threshold, we downsample the sequence of observations. And that allows us to use a 1 Hertz planning rate on that allows us a 1 Hertz planning rate on our aerial robots. Now the question is, how do we make it distributed? So let's say there are two robots in the environment, red and green, and red takes a depth observation. First, red runs a GMM of its own observation and transmits it to the green robot. Then the green robot updates its local GMM and updates its occupancy estimates based on the received GMM. And this happens asynchronously for all the robots in the framework. Notice how the communication is being handled here. We are not transmitting occupancy bits at all. We are only transmitting Gaussian mixture models, whereas the occupancy is being reconstructed locally on the robots. This is the key part of allowing us to operate with a low communication bandwidth. So we evaluated this system with two robots in a cave in West Virginia. The two robots are shown on the left. These are small aerial robots. And again, recall that the experimental scenario is motivated with the concept of operations that I outlined earlier. The robot shown in the image has a real sense on it and a downward blue fox that I'm gonna show in a bit. Yeah, so it has a downward blue fox with which it estimates its state. The state estimator is not the contribution of this work, but I wanted to make sure people are aware how we are estimating state. And the forward depth sensor is used for mapping. We deployed it in a cave, which has a very small entrance. So that's why the robot had to be small. And the cave features are shown on the right. It has significant breakdown. So that's why ground robots were not an ideal option. Maybe legged robots, but legged robots are mostly bigger than 90 centimeters in diameter. So we had to make a small aerial robot. And the cave environment, as you can see on the bottom right, has a lot of features in there. So the map has to really capture the fidelity to give us some useful data out of the map. So now the exploration system is as follows. Data from the PixRacer IMU and the downward shutter is used for visual inertial system. The pose estimate from the visual inertial system are used for, and the depth images from RealSense are used for GMM mapping. The local occupancy map derived from the GMM is used by an information theoretic motion planner, which generates our informative plans. And then these plans are followed by the trajectory tracker. The map information learned by this robot is transmitted over inter-robot comms over a UDP protocol via a Wi-Fi receiver that we have placed in the environment. And they are received by other robots, and the exploration system continues. So in the experimental trial, we put the 2 robots in the cave environments. We were there just to watch. We just had our hands on the emergency stop button, basically. And the robots were transmitting high fidelity maps to the laptop in real time. And as you can see in the flight, in the flight experiments, the robots are creating this map shown on the bottom, on the top left, with the red part being densely sampled from the red robot, the left robot, and the green part being densely sampled from the right robot. And this is being transmitted in real time on a laptop, and it's just created from the GMMs of the 2 robots. Let's look at some quantitative analysis of this work. So am I out of time? Just checking on the time.
Yes.
Okay, I'm gonna speed this up. So the key result here was that when there is no limit on the communication, the Gaussian mixture model and the occupancy grid approach work similarly. So what we see on this plot is the communication bandwidth transferred over time. However, when the bandwidth is imposed on the robots, the occupancy grid mapping struggles as expected because the amount of data is too big. And this allowed us to see that when the occupancy, compared to occupancy grid mapping, GMM mapping exploration approach performs at least 20% better when the transmitting maps is not an issue. So in future work, we want to incorporate 3 elements. We want to incorporate coordination, and we want to incorporate a hierarchical GMM mapping strategy so that the representation can be improved further. Thank you. I'm happy to answer questions since we are out of time and can discuss the details.
Thanks a lot. We have time only for a very quick question. You can see there a hand rising.
Thank you, Satish, for the nice presentation. I had a quick question on the frequency that was used to exchange the GMM information. What was the rate at which the GMM was exchanged between the 2 robots?
It was 1 hertz. Oh, sorry, it was 6 hertz.
6 hertz, okay. Okay, thank you.
Yeah.
Let's thank again the speaker, and it's now time for our panel discussion. So if all the speakers can come here and Xinji stay online. Okay, so one mic is here. Great. So I think it was a fantastic session, and I think one thing that strikes me is the heterogeneity of various systems that we have seen, both in terms of the capabilities, I mean, the kind of like ground, water, and air, but also in terms of scales. So I wonder if you, some of you or all of you can comment in terms of the scale of the swarm, or I mean, from how the scale, like from a few element through agent or the swarm, how this dimension changes the complexity of the system, how this can help, and similarly how the heterogeneity can be helpful or can be instead make things more complicated to handle. Who wants to start?
Yeah, I can start on the scale. I guess the initial challenge usually is the deployment side. There's one challenge in this deployment of, as you grow in number, how do you deploy? I think from the oceanography side, I guess you probably have a lot more experience deploying these over long periods of time, but that's usually one challenge with the aerial ones that we have. And then complexity-wise, like code-wise, algorithmic-wise, depending on the algorithm that you're using, that's another challenge. How do you scale? Are these decentralized or distributed algorithms versus centrally computed?
Also the communication, like if you start adding, scaling more and more on robots, you're basically just putting more and more channels of communication. So you're actually, your messages is going to have some delays and slack, and there is a moment that you don't have any messages whatsoever. So that's one of the issues, as you said. One of the advantages of having heterogeneous systems is that you can have a really powerful robot that is slow, he has a lot of computer power, and you can have these really light robots that they can go and map really fast, give you kind of like a prior map and give you that information so you can complete like semantic mapping.
Yeah, my project was a little bit different in the way that like it needs a pretty high bot count to work, but conversely, like adding bots to my project really didn't add much complexity at all. They all did the same thing they would have done anyway, just there were more of them running into each other. But yeah, I mean, I did notice, like, for my end video, at first it was hard for the boat to get moving because the density of robots was so high, no one could go anywhere. And then near the end, there wasn't enough robots to push the boat usably. So, like, there seems to be a sweet spot on density of robots, which is something that could be explored later.
Very interesting. Do you want also to comment?
What can I say about the scalability is there are a number of factors, including perception and computation. In computation, you would like to go more distributed approaches, but then the communication becomes a problem. You can go to decentralized approaches, then the accuracy becomes a problem. In terms of perception, you really don't want to be like rely on mockup or like GPS. You usually want to go with the more local sensing strategies. And I think you need to consider like all these fronts, and considering the heterogeneity and homogeneity, I mean, this has different benefits in different systems. For example, if you are doing a formation control with just drones, homogeneity is much better because you can actually replace all the drones instantly, or you can change the roles based on it. But if you have a kind of a navigation mission that you need to cooperate with the ground vehicles, then heterogeneity becomes important. I think you all need to evaluate this scale, heterogeneity, homogeneity based on the application-wise, and you should consider all the things starting from perception, computation to actuation.
Okay, and I'll provide, let's say, a somewhat different perspective based on our experience. So a couple of observations, especially when you run operations, let's say, in the middle of the ocean. Before thinking even about complexity, you just want to make sure that these are reliable, right? Because in the middle of the Pacific, there's not much you can do about it. So if you don't have reliability, there's not much you can do. So that's the one first thing. Another thing is, especially in these applications, I don't mean that this is general, we also use models and in some cases data simulation so that these can go into oceanographic models, because by doing that, you get a better sense for what needs to be kind of observed, and then you can use some of the techniques that were discussed before on a sort of a larger scale. So basically, collecting data, doing data simulation with the kind of oceanographic models or so, and then refining, let's say, your sampling strategy based on that. And that helps to decouple kind of some of these problems into more manageable sub-problems. There's also something that I think that we need to do, and we've been doing this for, let's say, since 2010, which is nothing like running real operations to basically understand what are the challenges. And we've been organizing since 2010 in cooperation first with the Portuguese Navy, now with CMRE in Italy, and NATO Center, and with the MUS initiative from NATO. So we've been organizing this large-scale exercise in which people from academia, industry, and the armed forces come together and run operations just to learn from experimentation what needs to be done, where are the bottlenecks. For example, to give you sort of a sense for the scale of this exercise, this year we had over 1,000 people, 17 navies, something like 80 ASVs, UAVs, and you name it. And one of the challenges there, very simple challenge that typically we don't think about, was interoperability, right? Because you have people bring some toys from this vendor, bring some toys from that vendor or so, and then, hey, these don't talk together. So, and this is pretty much what I wanted to say. Thank you.
Thank you. Very, very interesting perspective. Our speaker online, can you?
Yeah. So from a scalability standpoint, I think one of the things that we faced most challenge with was just communication. That was kind of the point of the work that I presented earlier. From an aerial robot's perspective, like if you really want to deploy 10 or 20 robots in a cave or an environment similar to a cave, what really matters is the robot is small, but at the same time, each robot has the communication capability that it can actually penetrate through meters of rock and boulders and stuff. So in order to deploy into environments such as those, I think scalability can only be achieved with kind of a co-design approach where the robot size is being minimized, each agent size is being minimized, but its communication capability is expanded. So I guess in that domain, scalability would only happen with respect to that. Or we do algorithmic optimizations with respect to just compressing our perceptual representations, or making sure we can just plan paths with respect to like different perceptual representations as opposed to occupancy grids, for example.
Yeah. So very interesting. It seems that communication and it seems to be for most of you the main bottleneck, which is quite interesting. We don't have any more time. It would be nice to keep talking for 1 hour or so, but the 5 people that are here can continue during lunch. And yeah, this is all for today, I guess.
Thank you.
Thank you.